When we're solving exponential equations, one of the sides of the equation, at least, is going to have an exponent, and that exponent is going to have a variable. So the key thing is we want to make sure that the bases or the big numbers are equal to each other. So when we're looking at the first problem here, the bases are the 6 and the 216. So you may be thinking, how in the world are we going to get these to be the same number? And really, it's about looking at the smaller number to start and seeing if we can raise the smaller number to a power to get the bigger number. So if we were to go in our calculator, we could do this with a scientific calculator. We could also do it with our phone calculator. Mine's a little dirty. Let me give it a little wipe there. So we could do 6, and if we want to raise it to an exponent, we would hit our exponent button, and we could try various powers of 6 until we get to 216. So I know it's got to be a little bit bigger than 6 squared. So I can try 6 to the third, which is 216. So we're going to rewrite 216 as a 6 to the third power. So we're rewriting the bigger number as a power of the smaller number. And then we're going to keep the side that has the smaller number already the same. So for properties of exponents, when you have the same base and, well, they're both the same number, you can set the exponents equal to each other. So we can go ahead and cross out the 6s and just set the exponent of b plus 1 equal to 3. And then all we need to do is solve for b. So we'll subtract 1 for both sides, and we'll get b equals, that'd be a positive 2. Thought it was a negative at first. So really, you're just solving for what would b have to be in order to get this number. You can also check your work, which is really handy, and you don't have to do this, but you can plug the 2 in for the b, and you'll see that 6 to the third power is 216. If you go in your calculator and you raise 6 to the third, you'll get 216. So that's just a little way you can check your work, which you don't have to, but sometimes people feel a little bit more confident after they do that. So this one over here has an 81 in the bottom. So we are going to definitely still look at the smaller number and the bigger number. Just go ahead and ignore that one on the top for a second, and I'll tell you what you have to do with it here in a minute. So if we look and we go in our calculator and we raise 3 to the second power, we get 9. 3 to the third power, just to kind of show you how you can do that. There's quite a glare when it comes to using that. There we go. So if you do 3 to the third, you'll get 27. And if we do 3 to the fourth, we get 81. You can do that in a scientific calculator as well, using the little button that looks like this. So we do, if we're doing that in our calculator, 3, we hit this button and we hit the 4. And since that is 81, we're going to replace the smaller, I said that backwards. We're going to replace the bigger number, which is our 81, with our 3 to the fourth. Now, since that 81 is in the bottom, that means that it's the inverse of 81. And we have to put a negative with this 4. You actually might remember from a previous lesson that anytime we have a negative exponent, it causes the number to live in the bottom of the fraction. So 3 to the negative fourth is the same thing as 1 over 3 to the positive 4. which is 1 over 81. So that's just how we know that -4 is gonna occur, because that 81 is living in the bottom. We're gonna keep this expression the same because it already has the smaller number or smaller base. And then we can go ahead and cross them off and set our exponents equal to each other. So 3v equals -4. We can divide both sides by 3. And if it does not divide, let's go ahead and just leave it a fraction. If you want to reduce it, standardized tests might have that reduced. You can also reduce it using your calculator, but you don't have to for our class. So when we look at this third one over here, we have our base of 9 and our base of 81. So the smaller base, typically, you want to check if the smaller base can be raised to an exponent to get the bigger base. So since 9 to the second power is 81, we can replace the 81 with a 9 squared. And we're going to drop down our regular base of 9 over here and our exponent. Now, when this happens, this 9 squared has replaced the 81, but this 2 minus p has to carry down in a parenthesis. So any like pre-existing power just needs to drag down. Once the bases are the same, we can cross them out and we can set our exponents equal to each other. You can put an invisible 1 in front of that p if you would like. We'll use our distributive power. So 2 times 2 is 4, and 2 times -1 is -2p. We'll move our letters to one side. I'm going to add that 2p over to the -3p. Carry that over here. We're going to keep our 2. -3 plus 2 is -1p, or just -p, and we have our equals 4. To isolate p, we'll get rid of our 2. We'll do the opposite, which is subtraction. And 4 minus 2 is 2. Since this is a -1p, you can divide by -1 and get a -2 for p. I didn't check the work on example number 2 or 3, but you could plug your answer in as the power for p up here to check your work and make sure you get equivalent expressions if you would like. It would be a little trickier with a fraction, but it is possible. So I want to talk about what would happen if the smaller base raised to an exponent is not the bigger base. So 27 is already a pretty big number. And if we square 27, it's definitely going to be bigger than 81. So I just went and checked in my calculator, and 27 to the second power is already way bigger than 81. So we want to look for a number that can be raised to a power that gets me these two numbers. It's really a game of guess and check. I like to tell people if they're odd numbers, trying 3 or 5. And if they're even numbers, maybe trying 2, 4, maybe 6 or 8. And so what you can do is when you go to use your calculator is, since it was 81 and 27, you can play around with the first odd number 3 other than 1. Raised to the second, and we see that's 9. And if we go in and we raise 3 to the third, we have 27. So that's kind of good to know. And if we raise 3 to the fourth, we get 81. So we're going to go in and replace our 81 with 3 to the fourth and carry down our old exponent. And we're going to replace 27 with 3 to the third, carry down our old exponent. Once these bases are the same, we can cross them out, and then we can go to solving. Now you already have these parentheses set up. So if you want to go right to the distributive property, you can. So 4 times -1r, you can put a -1r there if that's better for you, is -4r. And 4 times +1 is +4. 3 times 3r is 9r, and then we're good to solve. The letters are on the right, so I'm going to go ahead and carry over the 4r with the 9r, since there's only letters over here. Drop down my 4, 9 plus 4 is 13 with the r, and divide by the coefficient. So r is 4/13. Another one that might be hard to double check because it's a fraction, and plugging in a fraction for r may be difficult, but it is possible to do. So a little bit trickier, you have to find that base that can be raised to an exponent. The exponents don't have to be the same, but the base has to be the same. This would be another good example here. 16 raised to the second power is too big of number, but both of these numbers are existing powers of 4. So it takes time to kind of figure out what numbers you can use, but you can use any number raised to a power that equals either of these. So it turns out that 2 would also work, but I know that 4 squared is 16, so I'm going to use that one because 4 squared is 16 and 4 to the third is 64. But you could also use 2, I believe, because 2 to the fourth is 16. And let's just check that 2 to the sixth is 64. Yep, it does work out. So you can really find whatever base works out for you. We're going to drop our old power down in parentheses right next to the new power, and only the bases get crossed out. 2 times -x, you can make that a -1x if you prefer, is -2x. And 3 times -3x is -9x. All the x's, it's all only x's here. So you can choose which side you want to bring them to. And we have 0 as a placeholder, divided by 7, x equals 0. So you're probably starting to get the drift of how to do these already. Sometimes what I like to tell people is sometimes there's an existing power, sometimes there's not. So if you have a number that doesn't have an exponent, just know that you're only going to be using your new power. So in this case, your new power is 2, since 2 squared is 4. I decided to use 2 because 32 cannot be rewritten as a new power of 4. For instance, 4 squared is 16, but 4 to the third is too big. But 2 to the fifth is 32. So when this happens, we drop down our old power if we have one, cross out our base, and then set our exponents equal. So 5 times 3a is 15a. Drop our new power down of 2. Divide by 15. And we have a equals 2/15. No need to reduce or divide unless you really want to. If you wanted to see one more with a fraction, just to make sure you feel really comfortable on it, we can do number 7 as well. So for this one, 6 and 36 are the bases. Now 36 is a power of 6. 6 to the second. So those are always really convenient when the smaller number is a power of the big. It's a little easier to figure out, in my opinion. But it doesn't always happen that way. Drop down your old exponent. Now here, this 6 is living in the bottom, so we got to make sure we put a -1 as a placeholder. Cross out our 6's. Maybe write yourself a note here that it's a negative exponent if the base is in the bottom. So we'll go ahead and set our exponents equal. And we'll distribute our 2. So we'll have this our -1x, so -2x minus 2 equals -1. Add our 2 over. -2x comes down. -1 plus 2 is 1. Division at the end. Negative and negative cancel out when you divide. And that leaves us with a -1/2. That negative can just come out front, or it can stay in the bottom. So this is a little bit of how we solve exponential equations. And if you have additional questions or need to see additional examples, just let me know.